Hey, today I want to show you two new things we actually built in the GeoDN space. So GeoDN stands for Geospatial Discovery Network, which is a tool suite for geospatial data processing and analysis, which we are building. And there are two components which I want to show you today. It's GeoDN Workflow and GeoDN Tensor Lake House. So let's start with the challenges we are addressing here. So we need to do data integration at scale. That's why we need to have scalable workflows where we download, transform, harmonize, index, and clean geospatial image data. We can do it at petabyte scale. Then we want to do data and ML ops. So we want to always know what data has been processed by whom, which code was used, and also in case we train a model on top of the data, we want to know which version of the data has been used for a specific version of the model. So we have complete model and data lineage. So we bridge the gap between visionary research and software engineering principles, because we have very skilled researchers. So we have atmospheric physicists and all those guys. No, they code, but we need to make sure that this code is production ready. That's why we have a pipeline, a CI/CD pipeline, which takes care of various tests and deployment and automation and so on. Then we have big data discovery at scale. So that's our Tensor Lake House. It's actually accepted for IEEE big data, taking part in December 2023. And there we actually allowed to identify, find and subset, transform and visualize image data at petabyte scale residing in different federated data lakes. And then we have data sampling and serving for foundation model training. That means actually that we need to stream sample batches to GPU clusters as fast as possible, with the caveat that we just need to identify the correct tensors, and that is something really special, I think, in our implementation. And finally, we have data gravity. That's a problem now, because as I already mentioned, we have federated data lake houses, so we cannot transfer those petabytes of data between data centers. So we need to actually push computation to the source data. So for the workflow platform, we actually run on top of kubeflow, which runs on top of Kubernetes, in our case on OpenShift. And before we have done this, we had a lot of inconsistencies. So we didn't catch all the errors which happened during processing. We had a lot of manual steps. So people have been the single point of failure when someone was on vacation. The other one needed to take over and didn't know what to do, kind of, no. Manual steps are of course error prone, and also it was slow because maybe the guy was not available, or then there was a time zone difference and so on. And also it was hard to actually track who did what to actually reconstruct the data processing pipeline in case needed. So our solution is relatively simple but straightforward. We use kubeflow. We have a mechanism in place to create those kubeflow components easily. I'll talk about that in a second, but that actually gives us scalability, repeatability, reusability, because the KFP components can be used, of course. We can compose workflows through the components. It's fully transparent who did what and which code was used. And that actually gives us data lineage for free. And if we just store the pipeline ID, which was responsible for data set, then we also can even push it down to model lineage. So we have also GitOps and MLOps in place. So that means actually the code the researchers are writing, we need to sometimes review it, but the idea is we can go from Python R on notebooks via the C3 compiler of Claimed, and that compiles directly to kubeflow pipeline components or to Kubernetes jobs. We can run the code from the CLI. Also, we plan to support different job schedulers like Slurm and LSF. And also at the moment it compiles CWL, so Common Workflow Language tasks. So the compiler basically takes a look at the code. It creates an interface based on the variables you read, like the environment variables. It also is aware of the requirements. So using the requirements, the Docker image is created and then pushed to a registry. And then to that registry entry, the different deployment YAML files actually point to. Now in a kubeflow pipeline or Kubernetes job, you have a image source, and that's something we automatically generate, including all the interface. This happens automatically. So if you push the code, then this whole pipeline gets triggered and the artifacts are built and pushed to the respective repositories. And note that the claimed project has more than 2,000 stars, so it's quite a growing project. So I put myself a little higher. So, okay, so what happens as well is we create a grid computing mechanism on top of all the components or tasks we generate. That's basically done via a decorator pattern. So we encapsulate the actual container or code, and the coordinator code is also part of the task now, and the only central thing we need is a file storage where we actually store state. That can be on Cloud Object Store or also on local file storage, and it can also work in hybrid scenarios. So we had cases where we had workers on local data centers, on serverless execution engines like IBM Code Engine, and on OpenShift clusters. And this is all for free because the code is automatically generated anyway for all the components we built with the C3 compiler. The only thing you need to specify is the partition scheme. So you can either have a regex or something similar, or Python code which we inject into the component, which actually groups together files into partitions, which we then process together. Or you can also provide a list of files. And you can think of this as a map face in MapReduce, but you don't need any of those APIs. So you don't need Hadoop, no Spark, no Dask, no Ray, nothing. You can use the non-scalable libraries. In our case, we use a lot of GDAL and Rasterio, which are not scalable out of the box. And this way it's coming for free. And going to the data lake or Tensor Lake House, we actually have built on top of a lot of open source and some glue, something which is pretty unique, I would say. So we have support for different file systems. So we have here Ceph and Lustre and all those for local data centers, and also S3 and Ceph support for cloud data centers. And what we actually do is we store a specific file format, or at the moment we are using two specific file formats. It's actually COG, Cloud Optimized GeoTIFF, or zarr. So zarr is something like Parquet, but it's actually capable of storing multidimensional tensors. And here we have COG, which is Cloud Optimized GeoTIFF. And in those two cases, the key property is that meta information about the contents of the file is stored in the header of the file. And that way, if they reside on Cloud Object Store via HTTP range reads, we can just read the header, and then we know the contents of the file, and then we can read and directly address subblocks in the file without reading the whole file now. And in order to know what we want to read, we have here used Stacks, Spatial Temporal Asset Catalog. In our case, we run a version on top of PostGIS. And that way we can query the whole hypercube, and based on our query we can extract subcubes or subtensors from the hypercube. That's actually what we can do. And then it boils down to find the file in Cloud Object Store and open the header, and from there compute the offset and request via HTTP range read the specific block. The cool thing is that's all done for us for free, kind of. No, we are using xarray, and we are running xarray on top of Dask, and that's actually possible in xarray. But on top of that, we also use openeo, and openeo actually gives us back a data cube API, and it queries the stack catalog, and then actually uses xarray to read the data from zarr or coq and return back the subtensors. Another thing is, since we're using openeo, we can actually do federation for free. So openeo basically creates an execution graph. This is out of the box one-to-one map to a task graph. But what we obviously can do is we can slice and dice the graph, or we can just cut it at specific points where we expect a region of low data transfer, and then we execute the subgraphs on different backend systems which are running this stack or another openeo stack. That's how federation is done easily. And the other thing is we implement tensor streaming functionality, which allows us for debiased sampling, but I will come to that in a second. And here you see we actually got accepted at the IEEE International Workshop on Big Data Analytics for Climate Change. It's in December this year. So this is about the debiased sampling. I really need to get rid of myself somehow. So, okay, so this is actually based on a hierarchical statistical index, which allows us to compute aggregates, so different statistics at different resolution levels. And that way, for example, here we have an example for population density. Obviously, it doesn't make sense if you train a foundation model with only image data from oceans. No, that way we can debias the data and say, okay, please return us more samples from highly populated areas and less from less populated areas, and nearly nothing from ocean. No? And that's all running out of the box and basically is streamed to PyTorch. And here we have an overview how we address data gravity. So in the simplest case, we use the centralized stack index. We can federate over it, but we at the moment have a centralized one. And what we do is we integrate different data sources. So we have some sort of a plugin architecture, and we can pull data from COS, from Cloud Object Store S3, but also from HBase, or in the near future also from SQL engines. And that way you have a centralized view on top of all data, and you really don't care where the data is coming from. So you just query by time box and by bounding box. And what you then get is a subcube of the hypercube you are querying on, but you don't actually know where the data is residing and came from. Okay, I think that's it. If you have any questions, please post them in the comment section below. Thanks a lot for watching. Take care and see you soon. Bye.